Hello everybody. In this video we are going to be going through an example problem with a heat engine cycle. So we're going to get a bit more computational, a bit more quantitative with this example. Now hopefully this example helps shed some light on anything you still may be confused about. But as a reminder, if you are still confused after this video, please feel free to drop into my office hours or shoot me an email, and we can figure out I can help you out to see what I can help clarify. So here's the problem. We have an engine, and this is the cycle that it goes through. It starts with a compressed state, which is 1 liter in volume, and the gas inside of the piston is a temperature of 427 degrees Celsius, and the pressure is 900 kilopascals. The piston then expands at a constant pressure to a volume of 3 liters. The gas's pressure is then reduced to 400 kilopascals while the piston remains in place. The piston then compresses back to a 1 liter volume, maintaining this new lower pressure. The gas's pressure is then increased back to the original 900 kilopascals while maintaining the piston at a fixed position. Our goal is to analyze the energy transfers between each of these 4 states. I want you to think about why it's 4 states and not 5, even though we had a process that was A, B, C, D, E here. And then I want you to use energy bar charts, a PV diagram, to aid in your analysis there. And I'm going to walk you through how to do that more specifically. The next video, then, we're going to look at this engine from this problem and look at its efficiency and determine on whether or not it's a good engine. A little spoiler alert, it's not a great engine as far as efficiency goes, but it is a good starting place for an example problem. All right, so here is step 1. We want to use the ideal gas law and our equation for total internal energy to determine the properties of each of the 4 states mentioned in that cycle. So we've got our ideal gas law, PV equals nRT, and the internal energy is nRT is our equation for internal energy. Remember, T is how much energy one particle has, multiply something related to how many particles we have altogether, and you get the total amount of energy for all of the particles. So anyways, let's go ahead. I like to have an organized list of each state and all of its state variables. So here we go. State A, pressure, volume, number of moles in the gas, temperature, internal energy. Those would be the state variables for that state. We know state A is at a pressure of 900 kilopascals. It's at 1 liter, which is 1 times 10 to the minus 3 cubic meters in SI units. We don't know how much gas we have, but we do know its temperature is 427 degrees Celsius or 700 Kelvin. And we don't yet know the internal energy. From state A, we went to state B. State B stayed at that same pressure, but it expanded to 3 liters. Don't know any of this. State C reduced pressure to 400 kilopascals, but it maintained that same volume at 3 liters, or 3 times 10 to the minus 3 cubic meters. State D, we maintain that low 400 kilopascal pressure, but we contract back to the original 1 liter volume. And the reason that there was only 4 states and not 5 is that that last step was just mentioning how we got back from state D to state A. And so it was just a 4-state engine because we went from A to B to C to D and then back to A. So here's what's given. This is just the list of givens right now. We can use these equations to figure out these unknowns. I'm going to ask that you pause the video, see if you can compute those on your own, and then after you've done that, unpause the video and check your answers against mine. So I'll give you the chance to do that now. All right, assuming you've paused the videos and given it a chance to compute, let's see the best way to go about this. State A is the best place to start because there's only one unknown in the ideal gas law, which is the amount of gas. So we use PV equals nRT, and we end up with 0.1547 moles. And then we recognize that the amount of gas inside of the chamber, inside of the cylinder, does not change. It's the same amount everywhere. So this number carries across there. We can then also use the ideal gas law to come up with the temperatures for the other 3 states once we know the amount of gas. And so those are listed there. And then finally, the internal energy is a function of the temperature and then how much gas we have, and that's known for everything now. And so we now have the internal energy. A few things to note: the energy inside of the gas increases from A to B. We get to a really hot temperature there. And then as we reduce the pressure, the temperature lowers. And as we reduce the pressure and the volume, the temperature lowers further. So just pay attention to those variables. So this is the summary of the data that we are given. Now, how do we use this to analyze the transfers that happen between these states? Let's take a look. So we want to sketch a PV diagram in the center of the page. This should take up an entire piece of paper, what we are about to do. In each corner of the page, we want to sketch the piston so we get a picture of what the piston looks like at that state. And we want to draw a bar chart representing the internal energy of the gas inside of the cylinder. Between each of the states, we want to draw a system flow diagram to represent the working and the heating, those energy transfers. And then we want to use the PV diagram to compute the amount of working, and then any other energy changes that weren't accounted for through working must be accounted for through heating. And so that's where the first law of thermodynamics comes in. So this is our general process. I wanted to give you the overview, but it'll make more sense, I think, once you see it in action. So let's get started. Center of the page, PV diagram. I'm going to use pressure in kilopascals and volume in 10 to the minus 3 cubic meters because we're going to eventually look at the area under this curve. And when you multiply kilopascals by 10 to the minus 3 meters, the 10 to the 3 and the 10 to the minus 3 sort of undo each other, or they multiply to 1. And so we'll end up with SI units looking at the area underneath of this graph. So anyway, here we go. 4 zones. And we're getting to the point where I'm going to be in the way, I'll be in the least amount of, I'll be the least distracting here. Actually, can I get rid of the bubble? I'm going to do that. All right, so now let's go ahead and take a look. So what does this graph mean? The bottom left corner here is low volume, low pressure. The top left corner is low volume, high pressure. This upper right corner is large volume and large pressure. And this lower right corner is a large volume but a lower pressure. And so we've got sort of I don't want to say quadrants, but 4 zones in this graph. And we are going to represent each of those 4 states with which of those 4 zones they land in. So let's start here in the top left corner. This is our low volume, high pressure state. That was state A. So it's in the top left corner of the graph. We're going to put state A in the top left box up here, state A. Now let's move along. State B was in that high pressure, the 900 kilopascals, and that high volume region of the graph. So we're going to put state B over here. And then state C maintained the large volume, but was at a lower pressure. So state C should be this green box. And then state D, it was at the low volume and low pressure. So state D should be in this lower left-hand corner. All right, so we want these 4 boxes to represent those 4 zones inside of the graph. And now let's get started with our sketches of the piston. State A was the compressed gas, a small volume at the high 900 kilopascal pressure. So let's go ahead and put that point on our graph. It's at a 1 liter volume and a 900 kilopascal pressure. That's where state A lands, right there. All right, now let's look at the internal energy of state A. Draw a bar graph for that internal energy. I'm going to arbitrarily make it 2 bars tall, and that corresponded to a temperature of 700 Kelvin or an energy in kilojoules of 1.350. We're going to use kilojoules as our energy unit because we are in the thousands of joules. All right, so that was state A. Let's look at state B now. The piston pushes forward. That's our power stroke. So the volume is now larger, but we're still at that high 900 kilopascal pressure. So we're at that 3 liter volume, but at the 900 kilopascal pressure. There's point B for state B. Let's look at the internal energy there. There is going to be a lot of energy in this state because it was 2100 Kelvin from our computation on the previous slide, or 4.050 kilojoules, which is exactly 3 times as much as we had before. So we're going to represent that with 3 times as many blocks here. Now, let's look at how we got from A to B. There are any of a number of possibilities for how we got there, but the way we did get there was maintaining a constant pressure, which looks like a horizontal line. And we want to orient that curve. We want to say I went from A to B and not B to A. So I'll put an arrow on that line. And now I want to represent that transition from A to B with a system flow diagram. So this circle is going to represent the system being the gas that's in the cylinder. And then outside of the system, we have the piston, which is this blue part here, the thing that we're pushing on. And we have the environment, which is the other gases surrounding on the outside. So let's think about what happens here. Well, working is leaving the cylinder and going into the piston. We're pushing the piston forward. We're sending energy out into the world through that piston, through that power stroke. So the working that's done from A to B is leaving the system. I'm going to represent that as just one block. How much working? Well, that's the area underneath of this graph. So we've got the 900 kilopascal pressure, and this area is going to give, or sorry, it's the negative of this area that gives us the working that's done, because this area is going to be a positive value, but working is leaving the system, and so we get that negative sign. For this situation, we're going from left to right. The volume is expanding. The change in volume from state A to state B is an increase of 2 liters, of 2 times 10 to the minus 3 cubic meters. 900 kilopascal times 2 times 10 to the minus 3 cubic meters overall gives us 900 times 2 is 1,800 Newton meters of work. Put the negative sign out front because we're losing energy to the piston. Putting this in our system and keep maintaining that kilo prefix that we're using all around this drawing, the working there is negative 1.8 kilonewton meters. All right, great. So that looks good. But right now our picture isn't complete because we started with 2 blocks and now we just lost energy, and now we ended up with 6 blocks in the end. So where did that energy come from? Well, there must be heating that's done to add energy into the system. Otherwise, we would also lose pressure during this stroke. So the heating is done to maintain the pressure. So the environment, maybe there's a flame or something, I don't know, heats the cylinder. We represent that as 1, 2, 3, 4, 5 orange blocks here. There's Q heating from A to B. And so we can see pictorially with this picture, 2 red blocks, lose 1 red block, add in 5 orange blocks, we end up with 1 red block and 5 orange blocks. So that's sort of the representation here, but how much heating is done? Well, we need to answer this question. We start with 1.35 kilojoules, we lose 1.8 kilojoules, we add in some amount, and we end up with 4.05 kilojoules. That's an algebra problem. 1.35 minus 1.8 plus Q equals 4.05. So we just need to figure out that Q. If you do that algebra, you end up with positive 4.5 kilojoules for that heating. All right, we've now looked at the energy transfers from A to B. We just need to do every other state now and every other transition. So let's look at state C next. State C has less energy than state B. It's at 1.8 kilojoules of internal energy. It's still at that expanded volume, but it's at the lower 400 kilopascal pressure. Where does that live on our PV diagram? Well, 400 kilopascals of pressure here, 3 liter volume. There's state C on this graph. All right, cool. And we went from B to C along a line where we maintained a constant volume. There was no volume change. So with that, let's look at our system flow between B and C. Again, our system consists of the gas that's in the cylinder, and we have the piston and the environment outside of our system. Well, let's look at the working that's done from B to C. What is the area underneath of a vertical line? Well, a vertical line has no width to it, and so the area here is 0. There's no working that's done. Another way to think about that is this piston wasn't pushed anywhere. It stayed where it was at. And because there is no displacement of the piston, there's no working that's done. So all of the energy transfers must be through a heating process. In fact, it's the gas that's in the cylinder that's heating the environment, not the other way around. We are losing energy through the heating process. And we represented that as 3 orange blocks leaving the system. So that's the heating from B to C. And we again have this algebra problem. We start with 4.05 kilojoules, we lose some amount, and we end up with 1.8 kilojoules. How much should we lose? The answer to that is negative. We lost 2.25 kilojoules, or it was a negative heating because it was leaving the system. So again, 4.05 plus negative 2.25 equals 1.8. That's where that number comes from. And there's no working that's done because the piston stayed in place. All right, we have 3 of our 4 states. Let's look at the last one now. We are at the low 400 kilopascal pressure. We are at the compressed volume, and we are at a very low internal energy of just 0.6 kilojoules, which corresponds to a temperature of 311.1 Kelvin. And point D lives here on our graph. It's at the low pressure and the low volume range. And we transition from C to D, so we'll draw in our line with our orientation for that path. Let's look at the system and the flow that's there. Our system consists of the gas in the cylinder, and outside the system is the piston and the environment. We're adding energy into our system now by compressing that gas. Compressing the gas is actually a working process that adds energy into the system. Now, let's take a look at how much working is done. This time we're going from 3 to 1. The change in volume from C to D is not a positive 2 times 10 to the minus 3 cubic meters, but instead a negative 2 times 10 to the minus 3 cubic meters. And so if we take 400 times negative 2, that's going to be negative 800. And then the working is the negative of that. And so the working is a positive 800 joules, or a positive 0.8 kilojoules. Or in working, the way we usually write units for working, positive 0.8 kilonewton meters. We've added energy into the system through working. Notice we've got this area here shaded in, this blue top left to bottom right diagonal. That's for process from C to D, and all of the orange diagonal from A to B all the way down to the axis is this orange diagonal, is the working for that process. So pay attention to that. Now, we added energy in through working, but overall from C to D, we have less energy. So we must have lost energy through a heating process. The gas was cooled, in other words. So we're going to take out some energy there. And we end up with the heating from C to D. And again, we've got this algebra problem. Start with 1.8. We add in 0.8. We remove some amount, and we end up at 0.6. The amount we removed through heating must have been 2 kilojoules, or the heating was a negative 2.0 kilojoules there. All right, almost done. We just have the last transition back from D to A to look at now. So D to A, throw that line in there. In our system flow diagram, we have no working that's done because the piston stays in place, or we look at the graph, there's no volume underneath a vertical line. And so we're adding energy in through heating. And from D to A, the amount of heating we did, let's look, we started with 0.6 kilojoules, we heated it a bit, and we ended with 1.35 kilojoules. The amount of heating must be 0.75 kilojoules. All right, let's take a breath. There is a lot on this graph, but on this picture, but it represents all of the transfers between all 4 states, both heating and working, that is done. So please let me know if you have any questions. When you're looking at heat engine cycles, this is the sort of analysis that I expect, this level of depth. I expect the bar charts for each of the internal energies. I expect the sketch of the piston so we can see what it actually looks like. It helps me with a visual. I expect these system flows between each of the states, and I expect a PV diagram where you are describing the working that's done between each state. If you have any questions, please let me know. That's going to conclude this video. Thank you for learning with me, and I will see you in the next video.